So let's finish up this week with a quick discussion of the regulation of fatty acid synthesis. So if we go back to our overview of the interconnection of our glycolytic pathway, our TCA cycle, and fatty acid synthesis, the regulation of acetyl-CoA carboxylase will be our focus here. This is our regulatory enzyme, again, of fatty acid synthesis. So our regulatory enzyme, acetyl-CoA carboxylase, can be regulated by both allosteric as well as hormonal means. Initially, it's found as an inactive dimer in the cytosol. And as citrate levels in the cytosol elevate, this stimulates its polymerization into an active enzyme. So citrate is an allosteric activator of this process, where it stimulates the activity of acetyl-CoA carboxylase and therefore the production of malonyl-CoA. In contrast, palmitoyl-CoA, the product of fatty acid synthesis, will inhibit both the transport of citrate into the mitochondria as well as enzyme activity by stimulating the depolymerization of the enzyme acetyl-CoA carboxylase. So citrate is an activator of acetyl-CoA carboxylase, whereas palmitoyl-CoA is an inhibitor of the activity of the enzyme. So for hormonal regulation, we know that this is a fed state pathway. So it will be active when insulin is high. So acetyl-CoA carboxylase is active when dephosphorylated. In that case, it'll produce malonyl-CoA, and we'll get fatty acid synthesis. Conversely, in the fasted state, when glucagon is high, this will stimulate the production of the second messenger cyclic AMP and activate our AMP-dependent kinase. The kinase, once activated, will then phosphorylate and inactivate acetyl-CoA carboxylase. This inactive enzyme is phosphorylated and inactive. So again, this is another classic example of a fed state enzyme being dephosphorylated and active and inactivated by glucagon-mediated phosphorylation. So we'll finish with a question. And by now in the course, you must understand that I really enjoy reinforcing information from previous units. I think it helps connect biochemistry metabolically into a relevant context, and this is one of the types of questions. So if we increase the ratio of insulin to glucagon, the activity of which of the following enzymes is increased? So an increase in insulin to glucagon ratio will lead us to fed state metabolism. So what we need to determine is which of these enzymes is going to be active in the fed state. In the fasted state, we would expect gluconeogenesis, lipolysis, beta oxidation, ketogenesis, and protein catabolism to be active. The question is in the fed state, and in the fed state, we would expect glycolysis, glycogen synthesis, the pentose phosphate pathway, and fatty acid synthesis to be active. So let's look at what pathways these enzymes are active in. So hormone-sensitive lipase is our regulatory enzyme for lipolysis. So that's a fasted state enzyme. Conversely, acetyl-CoA carboxylase is our regulatory enzyme for fatty acid synthesis. Phosphofructokinase 2 is a regulatory enzyme for glycolysis, and glycogen synthase is a regulatory enzyme for glycogen synthesis. So we need these three enzymes to be active, and this enzyme, hormone-sensitive lipase, to be inactive. And that leads us to choice 4. Hormone-sensitive lipase is going to be inactive in the fed state, whereas our other three enzymes will all be active.